Now we're going to look at our three different transistor operating modes in a little more depth. So as a reminder, we can have our transistor in cutoff, active, or saturation. And our transistor looks like this base collector emitter. Okay, so when we are in cutoff mode, our collector emitter switch is open. And so we don't have any current flowing in the collector, and we don't have any current flowing in the base. So we can really just say, except for some maybe small currents that very small currents that we'll be able to ignore in 315, our currents are going to be, approximately equal to 0, we'll say. And between the base and the emitter, so our base emitter connection looks like a little diode. We saw this kind of in passing in the last video, but a lot of our analysis, we can kind of think about what's going on between the base and the emitter. Imagine that there is a diode here. Like, what would a diode do if it was connected between those? And that will tell us a little bit about what's going on. Okay, so our current equals 0 here, and our base emitter diode is off, meaning that it is either reverse biased, the emitter voltage is higher than the base voltage, or at least the base voltage is not 0.7 or more volts above the emitter. So VB is less than VE plus 0.7 volts. So the base voltage is not high enough to turn our diode on. Okay, and during this, the collector voltage can pretty much be anything. Of course, there are limits to this. If you're in cutoff mode and you have really big voltage differences in the reverse direction, like a diode, eventually things are going to break down. Transistors are more sensitive to breakdown effects than most diodes, and so you can damage transistors if you have these reverse voltages too big. Well, I'm not going to quiz you about that. So for the purposes of 315, our collector voltage can be anything here. Nothing funny is going to happen. If our diode is off, it's off, and nothing's going to happen to the collector. In real life, you should, think about these reverse voltages before you put 40 volts the wrong way across the transistor or whatever. Okay, so in active mode, we have our IC equals beta IB rule. So we have current going in the base, we have current going in the collector, and this is bigger than this by a factor of beta, and then we have the total of those currents. This is just Kirchhoff's law. The current coming out is equal to the two currents going in. But of course, if the collector current is 100 times higher than the base current, this is really approximately equal to the collector current. So if we only need our answers to be accurate to 1 or 2% or something like that, this is a reasonable approximation to make because B is only roughly 1% of C. Okay, for this to be true, we know a few other things. First of all, our base emitter diode has to be on, which means that our drop between the base and the emitter, so VBE, it just like a diode, it can't be bigger than 0.7. It is going to be at most 0.7, like trying to put a voltage across a diode. So VBE equals 0.7 volts. If we want our current to be flowing in the collector and out the emitter, it also has to be the case that our collector emitter voltage is greater than 0. So in other words, V collector is greater than V emitter. Maybe I'll write it that way instead. All right, so that's action mode. In saturation mode, now we have these currents flowing, but our collector is not able to provide as much current as this equation would have it. So in other words, we have a base current going in, we have a collector current going in, but because our base current is so big, IC cannot be 100 times that anymore. So IC is something less than beta IB. If it was able to be equal to beta IB, we would still be in active mode. Okay, so when this is true, our diode is still on. So that means we still have a base emitter drop of 0.7 volts. That is still true. These are the same, right? The diode being on means there's this 0.7 volt drop. And now, what's going to happen is that our collector and our emitter are going to be at almost the same voltage. For most transistors like these, there'll still be a couple tenths of a volt difference. You can buy, I think, fancy transistors where that difference is smaller, but for typical NPN transistors, VC is going to be equal to VE plus, we'll say for this class, 0.2 of a volt. So this is the smallest voltage difference you can have. The little transistor man has shorted out his collector emitter connection, but it's not quite shorted out. There's still some little resistance that still is giving you a little voltage drop between C and E. All right, so these rules are actually enough to analyze our transistor behavior pretty much entirely. There are a couple little odds and ends, but I think this is pretty much everything we need. So if we want to really analyze transistor performance, you can look at these things called the characteristic curves that plot different currents versus different voltages and kind of exploring the relationship between all of these variables. These are a lot of variables. They require multiple graphs with multiple traces on each graph. So we're not going to deal too much with the characteristic curves, but they'll probably come up again in the next couple lectures. So we'll be able to draw some graphs of what's going on in a little bit.